Leetcode 48, rotate image. It's a medium problem, but probably one of the easiest mediums out there, at least in my take. And here is the description. You are given an n times n 2D matrix, meaning that in Python, if you take a look on the right side, we have list of lists, and there is that outer list, which contains inner lists, and those inner lists are the rows when we are talking about the matrix. And n times n means that we have exactly same number of rows as columns, meaning that the matrix is square. And usually it is the case that when we have square matrices, then some calculations are simpler and some calculations are possible or certain operations become possible, as in this case, because we cannot really think about them in a case where the number of rows and columns differ. So certain operations on matrices are only possible when we have square matrices. And the next piece of information is that it represents an image, representing an image, but this is basically a noise in this whole problem. It doesn't bring anything to us, and that particular matrix could represent any kind of information, maybe currents or voltages or anything like this, or maybe just be an abstract mathematical structure, and it could carry no information whatsoever. So this doesn't influence the later course of action. And the next thing is our task: rotate the image by 90 degrees clockwise. So we'll have to rotate it like this and we'll talk in detail what does it mean exactly. You have to rotate the image in place, which means you have to modify the input to the matrix directly. So all the changes, all the manipulation on indices will happen on this input matrix, and we don't return anything. Do not allocate another to the matrix and do the rotation. And of course, I think that at least in this case, it's even easier to do it in place than to do it on some separate structure and think about matrices in the input and output separately. So I think that this is very very obvious thing to do, but the other benefit, of course, is that if you don't allocate any additional structures, you will use less memory, which is always preferred. And here is an example. We have the input matrix, which has following form. It starts with 1, the first cell, and then each cell to the right and then to the bottom is like incremented by 1. So 1, 2, 3, 4, 5, 6, 7, and 8, 8 and 9. And if we rotate it clockwise, then we end up with something like this. So what has happened? Look, this row at the top ends up being the column for the output, which is on the right side. So top goes to the right, and right column goes to the bottom, and so on and so forth. So it was just rotated by 90 degrees, and the middle element stays the same. So basically, there were two operations that happened. One is transposition. So it was transposed, the matrix. And the second is that each row was reversed after this transpose operation. And I will explain it in a minute, exactly how to do it and why is it the case, but just giving you this preview already. And the second example is on a bigger matrix, but it's basically the same thing. So as you can see, the top row becomes the right column. The right column becomes the bottom row, and inside, right now we don't have a single square in the middle or single cell in the middle. We have to also rotate those. So this inner matrix or inner square, as you may think about it, the top of the inner part was 4 and 8, and then it becomes the right column and so on. So the right column of this inner matrix 8 and 6 becomes the bottom part 8 and 6 here, and so on and so forth. So let's think about it and how can we solve that kind of problem. Let's copy it here to escalate row, rotate image, and we want to have 90 degrees clockwise rotation. So basically, maybe let's draw it like this. So we have different colors, and blue, and wait, let's do it like this. First, let's make two squares, and here rotation happens, and now I will add some highlights, maybe make it a bit thicker. So this top part becomes the right column. Yeah, the top row is turned to the right column. The right column becomes the bottom row, and so on and so forth. Yeah, so that's our rotation. And basically, as I said, we can break it down to two operations. Transpose, meaning swap matrix each cell on index I and j with the opposite, meaning matrix j and I. Yeah. So for each row and column, we swap it with its representative on the opposite side for the index in the respective row and column. We take I as a row number and j as a column number from the first cell, and we swap it with the one that would be on the same row as the previous one was in the column, and the column would be the same one as the previous one was in the row. Yeah, so that's basically transposition. And the second operation is just reverse each row. And if we do this operation one by one, then we'll arrive at 90 degrees matrix. So let's try to do it on that example. Let's make it a bit bigger. And after we transpose, so what will happen is that basically this whole diagonal, maybe let's move it a little bit. So off like this. Let's remove this one and put it here. So it's a little bit more visible. Yeah, so basically this diagonal stays the same. Yeah, it won't be touched, but everything on the opposite sides will be swapped. So 2 and 4 will be swapped. So 2 and 4. And 3 and 7. Yeah, so 7. And 6 and 8. 6 and 8. And if we just try to verify it, and then let's say we take 4 as an example. Yeah, so 4 has I of 1 and j of 0. Yeah, so here we take this element, f I equals to 1 and j equals to 0. Yeah, and it was swapped with 2. Yeah, which has Sorry, not this. And like this, and like this, and maybe then we can change the color, make it more visible. Yeah, and 2 has I equals to 0, yes, in the very first row, and j equals to 1. Yeah, and you can verify for everything else, but basically visually you can just leave this diagonal intact and swap everything that's on the opposite side. Yeah, and that's the transposition. And it's not yet, we are not yet done to rotate it 90 degrees. We need to do a second operation, reverse each row. And let's see what will happen after this. So we will have 7, 4, and 1, 8, 5, and 2, and 9, 6, and 3. And is it the expected output? Let's see. Let's copy it here. And looks like it's the same. Yeah, so basically we verified graphically that we can decompose this 90 degrees clockwise operation or transformation to 2 steps. And that's what we will do in the code. So let's do it. Let's first store n, which will be the number of rows. And because the number of rows equals the number of columns, we can just take the number of rows, and that's it. And now let's do the 2 steps. So first is transpose, then second is reverse each row, and basically for I in range n, and for j in range starting from I plus 1 till j and till n, sorry, we will do that operation. So matrix on this position and on that position will be swapped, and we can do work in Python in a very efficient way, like efficient in terms of writing. We can just do it in the following way: ji, and here I, j, and they're already swapped. And now for I in range n, the row will be matrix on index I, and we can simply reverse. I think that reverse is already defined in standard for lists, and it should operate on the same memory. I think that it will just modify it in place and not return a separate output. If not, then we will see it in a second. But let's just do it like this, or we can even make it shorter by removing this assignments. We don't need it. Yeah, and we don't have to return anything since we are operating in place. Okay, so let's see if it worked. It worked for 2 first cases, so now let's submit. And we beat 100% of the people, but almost everyone uses the same method, as you can see, so not many people use some different strategies since it's such a simple problem. But we can discuss about the time complexity and the memory complexity. So we have, or the space complexity, we have for time complexity nested loop, which is O(n) squared, yeah, and here we have single loop, which this would be O(n), but reverse operation would also be n, so probably both of those are n squared, which in total gives us n squared for time complexity. And we don't use any separate structures, meaning that we have O1 space complexity.